RSA encryption uses the product of two large prime numbers to generate a public key. This public key is used to encrypt information. Classically, the best known algorithms for factoring large numbers as the product of two primes takes exponential time. However, Shor's algorithm can do this in polynomial time. The algorithm converts a factoring problem into finding the period of a periodic function a to the x mod n. It's worth going over some modular arithmetic before we begin. So 5 divided by 3 is equal to 1 remainder 2, which is equivalent to saying 5 is equivalent to 2 mod 3. X is equivalent to 0 mod 3 means that x is a multiple of 3. X is equivalent to 1 mod 3 means that x is a multiple of 3 plus 1. And finally, x is equivalent to y mod 3 means that x is equal to 3k plus y, where k is some integer. Now we'll go over the protocol for Shor's algorithm. Step 1 is to pick a number a that is coprime with n. This means that a shares no common factors with n. Step 2 is to find the order r of the function f(an) is equal to a to the r mod n, which is the smallest r such that a to the r mod n is equal to 1. Step 3, we check if r is even. Then we set x to be a to the r over 2 mod n. If x plus 1 is not equal to 0 mod n, then our factors are contained in the greatest common denominator of x plus 1 in n and x minus 1 in n. Otherwise, we find another a. As an example, we will be factoring n equals 15, and we will choose our coprime a to be 13. We can graph the periodic function 13 to the x mod 15. Remember, we are trying to find the period of the function. That is, the smallest r such that a to the r mod n is equal to 1. Here, r is equal to 4. In our case, r is even, so we can compute x. X in our case is 4 mod 15. We want to check if x plus 1 is equivalent to 0 mod 15. In this case, x plus 1 is equal to 5 mod 15. From this, we can assume that p and q are contained in the greatest common denominator of 5 and 15, and 3 and 15. Now we have found our prime factors of 15. Let's say we had a larger a and a different a. It mightn't be so clear what the period of this function is. You might be able to eyeball it, but that's not what we're looking for. This is where Shor's algorithm comes in. The following is the circuit that implements Shor's algorithm for factoring n equals 15 with a is equal to 13. 15 in binary is represented by the number 1111. This is why we need 4 bits to represent our number. From here on, the top 4 bits will be known as the X register, and the 4 bits below it will be known as the W register. The circuit is quite complicated, so we'll take it step by step. The first step is to initialize all of our qubits to the 0 state. On the left, we have our qubits from the X register, and on the right, we have our qubits from the W register. Next, we will apply a Hadamard gate to the qubits on the X register. The Hadamard gate can be seen as a 1-qubit Fourier transform, which puts our 0 states into a superposition of 1 and 0. The subscript notation here is used to indicate that each of our numbers inside the kets is represented in base 2 using 4 bits. I won't explain it here, but essentially what UFAN does is implement our modular function. The circular symbol with the cross between it is the XOR operator, which is 0 if both bits are the same and 1 otherwise. Essentially what we've done here is apply a phase to each of our bits, which we can then measure using the quantum Fourier transform. The bits that have been highlighted are the bits in our W register. The only possible outcomes are 1, 13, 4, and 7. If we were to measure any one of the highlighted states, it would be no longer possible to measure any of the other states, which brings us to our next step, to measure the W register. As an example, let's say that we measure 7. The result of this simplification is because we are no longer able to measure 1, 13, or 4 anymore. Our next step is to apply the inverse Fourier transform on the x register. The quantum Fourier transform is defined as follows. The inverse quantum Fourier transform is created by taking the conjugate transpose of the quantum Fourier transform. So what we've done at this point is apply some Hadamard gates and the U-rotation box that implements a to the x mod n. And what our inverse Fourier transform is going to do is transform us back into the computational basis. So what we're doing here is just applying the inverse quantum Fourier transform on each of the bits in our x register. Now the inverse quantum Fourier transform of the x register as a whole is as follows. In the next slide I'll show you the short Python script I used to compute this sum. This step in the algorithm is probably the most important because it takes advantage of interference. You can see here that the sum only leaves us with 4 terms, which can be represented as follows. Now that we've applied the inverse Q of t, 0, 4, 8, and 12 are the only possible outcomes. Our last step is to measure the x register. The measurements peak for j times n over our percent integer j. Capital N is 2 to our number of qubits, which in this case is 4, so capital N is 16. So say for example we measure 4. Our measurements peak at 4, so the equation can only be satisfied if j is equal to 1 or r is equal to 4. Now, r is even, so we can compute x, and then we can compute x plus 1 and x minus 1, and finally compute the greatest common denominator using Euclid's algorithm. Now we have found p and q, which are our prime factors. Using Qiskit, we can actually run a simulation of the Shor's algorithm circuit and see what we get. This histogram displays the measured phases at the end of the circuit. Here we can see that we have measured phases of 0, 1/4, 3/4, and 1/2. After this, we can use the continued fractions algorithm to compute r. When using the continued fractions algorithm, the order r must be less than n, so I set the denominator to be 15. We can see that 2 of the measured eigenvalues give us a correct result for r, and it's worth noting that Shor's algorithm can fail. The code above reruns Shor's algorithm until a factor of 15 is found. We can see it takes a couple of attempts. If you're interested, this was actually done on a real quantum computer using 7 spin-half nuclei as quantum bits to factor the number 15. Anyway, thanks for watching. Hope you enjoyed.